All right, guys. I'm sorry to have to be out all this week, but I'm glad we get a chance to still learn a little something. I'll be back on Monday. And I want to keep this video short, hopefully 15 to 20 minutes, so let's just jump right into it. I know it's been a few days since we've been able to chat, so I thought it might be a good idea to quickly review what an arithmetic sequence is. And if you remember, a sequence in general, right, is just a series of, or I shouldn't use the term series, is just a pattern of numbers, right, or a pattern of anything. We've been using numbers. An arithmetic sequence, right, if you remember, is just a sequence, and let's just write this out, is a sequence that changes, by a constant d. Now, d just stands for what it's changing by each time, right? So an example, right, of an arithmetic sequence, I'll write it underneath, 1, 5, 9, 13, 17, dot, 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 right? The d value would be 4, okay, because it's changing by a constant. I noticed I wrote constant amount each time, right? So it's increasing the same amount each time. We saw an example in class before I left where slope, right, was kind of like an arithmetic sequence where the line was increasing by the same amount each time, right? So what I want to do now is think about a different type of sequence, and I want to look at these three sequences we have here. The first one being 2, 4, 8, 16, 32, 64, etc. The second one being 2, 1, 1/2, 1/4, 1/8. And the third one, 3, 9, 27, 81. Hopefully you all see a pattern there. Now notice the difference between each numbers each time is not the same, right? So for example, if we look at the first one, right, the difference between 2 and 4 is 2, 4 and 8 is 4, 8 and 16 is 8. So the difference between them is not the same, so it cannot be an arithmetic sequence. But what you may have noticed, at least in the first one, is that the number is doubling each time, right? To get the next number in the sequence, we're doubling the number. If we look at sequence number 2, to get the next number in the sequence, we're going to be dividing by 2 or multiplying by 1/2. If you look at number 3, we're multiplying each number by 3 in this case. So it's increasing by a factor of 3. The differences between the two terms is not 3, but to get the next number, you're going to multiply by 3, okay? So if I want to kind of think about this in general, I might say that in these sequences, the next term in the sequence can be found by multiplying, not adding like we did before, by multiplying the previous term by the same constant each time. Let's just call that constant r. So in the first one, I would say my r value is 2, because each time I'm multiplying the previous number by 2 to get it. In number 2, I might say my r value is 1/2, because to get the next number, I have to multiply my term by 1/2. And in the third one, I might say my r value is 3, because to get the next term, I'm going to multiply my previous number by 3. So while they're all different sequences, what they have in common is that we're multiplying the previous term by some r value or number to find the next term in the sequence. These are all examples of geometric sequences. So again, to repeat from above, an arithmetic sequence is a sequence that changes by a constant amount d each time. These are geometric, the difference being to get from one term to the next. In a geometric sequence, we need to multiply our previous term by r, which is what we did before. It's also called the ratio of the sequence, right? So r stands for ratio. So what I want you to do here on these 4 problems down below is to pause the video for a second and see if you can figure out which sequences are geometric and which ones are not. So pause the video, give it a shot, and circle which ones you think are which ones are geometric. All right, so hopefully you did that. And to give you a quick answer, okay, the geometric ones, this guy and this guy, no, no. And I think the easiest way to find that out is just literally plug in numbers. So for a sub n equals 2n, I might say a sub 1 equals 2 to the 1, which equals 2. Not a sub n. A sub 2 equals 2 to the 2, which equals 4. A sub 3 equals 2 to the 3 equals 8. So you'll notice the numbers are doubling each time. Where do we see a 2 in the problem? Right there. Interesting. If we look at the other one that I circled, 4 times 3 to the n, you'll notice that if you do the same thing for that, if you find the first few terms, you'll notice that it's tripling each time. A sub 1 would equal 12. Again, I'm just plugging in 1 for n. To find a sub 2, I'm going to plug in 2 for n. So 3 to the 2 is 9. 9 times 4 is 36. A sub 3 equals 108. So again, it looks like my r value here is 3, right? To get the next term, multiplying the previous value by 3. Where do I see a 3? Notice I see it there. So it would appear to me that the r value, or what I'm going to be multiplying to get the next term, is going to come from that number underneath the exponent. So you might say, all right, well then why wasn't this guy geometric? Well, let's do the same thing. A sub 1 would equal 3 because 2 to the 1 is 2 plus 1 equals 3. A sub 2, 2 squared is 4 plus 1 is 5. A sub 3, 2 cubed is 8 plus 1 is 9. I can already see that what I need to do to multiply 3 to get 5 is not the same thing to multiply 5 to get 9. So that doesn't work. And what really screws it up, guys, is this plus 1. Okay? If you're going to have a geometric sequence, not only do you need some number raised to an exponent, some number to the end, if you're going to have anything else with it, you need to have some type of coefficient like we see over here with the 4. Any type of adding or subtracting screws it up. Okay? And if we look at the top right one, n cubed, you'll see pretty quickly a sub 1 equals 1, a sub 2 equals 8, a sub 3 equals 27. There's no constant or no consistent r value. No consistent r value, so that doesn't work. So what we're really looking for, if we're looking for a geometric sequence, right, is some term raised to an exponent, and then if we're going to have anything else additional, it's got to be some type of coefficient that we're multiplying. Can't have some type of an addition, so goodbye. All right, so that's kind of our introduction to geometric sequences. There is a general formula we can use, an explicit general formula, and it's pretty similar to arithmetic, which could be a good thing or a bad thing, depending on how you look at it. But I'll let you in on the little secret here. To find any term in a geometric sequence, we're just going to say a sub n, which represents, again, any term in the sequence. That's going to be equal to a sub k, okay, which just represents a value in the sequence. Much like before, it's not the term, it's the value in the sequence, times, and pay careful attention here, r, which again we know stands for the ratio, raised to the n minus k. K, right, being the place of this term. So the sample term you're putting, that a sub k, the place of that term, okay, place of this term, sorry, I can't talk and write at the same time. The place of that term is going to be in the exponent, is going to be that k value. Okay, so if you remember, we had something similar when we did our arithmetic. We had n minus k in parentheses. It's the same idea here. So again, to repeat what we have in black here, right, value of the term, what we have, or at least I underlined in red, that's the place of that sample term we're using. All right, so let's maybe do a couple of examples, and then it'll be time to go. So let's do some sequence problems here in the back. It says find the 12th term of the sequence 5, 15, 45, dot, dot, dot. In this case, I know it's geometric, okay, not arithmetic, because to get from 5 to 15, I can see that my R value is 3. To get from 15 to 45, my R value is 3. So I seem to have a consistent R value, thus it's got to be geometric. So if I just write out my general geometric sequence, a sub n equals a sub k times r to the n minus k. Let's now fill in the missing pieces to get my explicit formula. I'm going to have a sub n equals, now if you remember, a sub k is your sample value. So you could use 5, 15, or 45. Let's use 5. But you could use any one of them. Equals 5 times my r value, which in this case is 3, raised to the n is my variable, and then I'm going to subtract out the place, right, the place of this term I put in here. 5 is the first term, so I'm going to subtract 1. Now notice I'm not subtracting 5, I'm not subtracting the value of the term, I'm subtracting the place of the term. So this right here, what I have listed here is my explicit formula. So explicit formula. Now to find the 12th term, you'll need a calculator for this for sure. So have your calculator handy. A sub 12 would just equal 5 times 3 to the 12 minus 1. 12 minus 1 being 11. So 5 times 3 to the 11th. I'll give you a second to do it on your calculator. Okay, hopefully you got it. If you haven't got it, you can hit pause before I write the answer. But your answer would be 885,735. So a big number, but as you can see, it's certainly doable. All right, example 2. Let's see, do I want to do example 2? Let's do example 4, and then we'll call it a day. So pay careful attention here. It's a little bit trickier. So it says the third term of a geometric sequence is 100, and the fifth term is 25. Find the 13th term in the sequence. Okay, so this one's a little bit difficult because I'm not given sequential terms, so it's not really easy to see what the R value is. So I need a way to come up with what that R value is, and I'll show you a nice convenient way to do it in a way that we can apply every single time. So the first thing I'm going to do, just like I do every time, is just write out my general sequence without any numbers. So a sub n equals a sub k times r to the n minus k. And when we think about what do I know and what do I not know? Well, I have two sample terms. I have 100 and I have 25. Okay? And what I really don't have is the R value, and I need the R value to figure out what the 13th term is. So, here's what I'm going to do. I'm going to plug in a value for a sub n. I'm going to use the fifth term in the sequence, 25, and say 25 I know is going to be equal to some other term, 100, times some value r, raised to n minus k. And if you remember, n always matches the place of this term here. So what is the place of 25? What place was that? That was the fifth term. So I'm going to plug in 5 for n, again to match that term, 25. And then I'm going to subtract from it what value? Well, I'm going to subtract from it the place of the a sub k term. What is the place of 100? Well, 100 is the third term, so I'm going to subtract out 100. Okay, so just to repeat, where I got the 5 from was the place of this term, the 25, and where I got the 3 from was the place of the 100 term, which was 3. So if I do a little simplification, if I divide both sides by 100, I get 25 over 100 equals r to the 5 minus 3, or r squared. 25 over 100 is 1/4. equals r squared. And if you square root both sides, square root of 1/4 is 1/2. You would just take the square root of the 1 and the square root of the 4. The square root of r squared is r. So my r value is 1/2. So if I wanted to come up with a formula, I now have an r value. I could say in general, a sub n is equal to, and again, I can choose a sample term. I could choose 100 or 25. But since I already used this 100 here, why don't I use 100 again? So a sub n equals 100 times, now I know it's 1/2, okay, raised to the n minus the place of the sample term, the place of the 100, which in this case I know to be 3. That, my friends, is my explicit formula. So just to repeat, explicit formula. Now, using my explicit formula, I can find the 13th term in the sequence. So I would do a sub 13 equals 100 times 1/2 to the 13 minus 3. Don't forget 1/2 is just 0.5. So on your calculator, let's maybe just to repeat this, order of operations would suggest, or not suggest, would require you to do this first. So you have to do 0.5 to the 10, do 0.5 to the 10, and then multiply that times 100. And if you do that, if we round to, I don't know, 3 decimals, you get a sub 13 equals 0.098. Okay? So that's a lot. It's a little bit challenging for sure. But I think that's a good start. We can certainly review it our next class. For homework, you're going to work on worksheet number 7. Okay? I'm going to say, why don't you try all of them? Try all of them, because you can get started on it now. Hopefully you're in class with your classmates. You guys, can talk about it. Use the solution key on Canvas to help you. And I'll be in class on Monday, knock on wood, and we can go over any questions you guys have.